for the compounds that we're looking at, we have, and I'm going to try to emphasize this and say an atom versus a molecule. If we looked at nickel as an atom, it's going to be completely different than Ni, NH3, 6, 2+. So the system that we use to get an electron configuration for an atom is going to be different, or in this case slightly different than what we look at for a molecule. Because for nickel, if we looked at its electron configuration, if we look at the periodic table, nickel is element number 28. That means as an atom, we need to put 28 electrons into all the orbitals. And we're going to fill that in the lowest energy configuration possible. So nickel is going to have the argon core, and it's going to have an electron configuration of 4s2, 3d8. So the next compound that we look at is nickel NH3 6 2+. The ammonia ligand is neutral. So that means the oxidation state of the nickel, where the charge of that nickel cation has to be 2+. So the question is, what changes when we go from a nickel atom to a nickel 2+ cation? Okay? The obvious answer here is we're going to lose 2 electrons. Okay? Now, the not so obvious answer would be, which 2 electrons have to be lost? So if I'm nickel and I have all these electrons buzzing around me, right? Which electrons are going to be removed first? Okay, someone said the d orbitals. Anybody want to take another guess? The s orbitals, okay? So let's think about this. Everything has to do with energy when we're looking at these transition metal complexes or any type of molecule or ion or atom that has electrons in. So the easy answer is the electrons that are lost are going to be the ones that are the easiest to remove. Make sense? Right? So it's kind of like if I'm reaching in to grab an electron, I'm going to grab the one that takes the less energy possible. Okay? Another way of looking at it, that's looking at it from me going in and grabbing an electron and pulling it away. Another way to look at it is if I'm the nucleus down here, I have all my protons were positively charged. Okay? The electrons that I'm going to let leave are when those 2 electrons leave, what is the lowest energy configuration that I'm going to be left with? Okay? And it doesn't, you should never assume that the way we put the order the electrons in are the way that those electrons are going to leave in the opposite order. Okay? Because what happens here is that the 4s orbital is a really, really large sphere, like a basketball. The d orbitals, we're going to look at the different shapes of those. And it just so happens that the 4s orbital extends farther into space than the 3d orbitals do. If I'm a nucleus and I'm positively charged down here, and there's electrons buzzing around out here, if I'm really close to the nucleus, there's going to be a strong attractive force there. But the farther I go away from the nucleus, the easier it is to remove me. And when you have an atom versus an ion, we also have to take into account what happens with those ammonia ligands. So we're going to talk about this and the reason for why this is in probably sometime later this week or early next week. But when I write an electron configuration for a metal cation, I have to say that this is going to be argon 3d8. Okay? So the general statement that we can make here is it is easier or we can say it takes less energy to remove the 4s electrons from a transition metal. So therefore, when we write out an electron configuration, we're always going to remove those s electrons first. This is the reason that practically every transition metal along the transition metal series has a 2+ oxidation state. Because for it to become a 2+ charge, it has to lose 2 electrons. So transition metals occur in varying oxidation states. The main reason that all of them, or most of them, have a 2+ charge is because it's like, hey, get those electrons in that s orbital out of here. So they're gone, and then we have to analyze a little bit more to figure out if it's a +3 and a +5, or a +4, or a +6, or anything like that. So this is the thing that we have to analyze, and this is the general rule that when we're looking at these complexes, it's easier to remove the s electrons. So when we're looking at the d electron count, which is very, very important for color and magnetism, we need to recognize that. Okay? So we can do the same thing then for the cobalt 2+ and the zinc 2+. All right? I'm going to go through and do zinc. If we looked at zinc as an atom, it's going to be argon 4s2 3d10. When we have zinc 2+, we have argon 3d10. And what I want you to try to recognize and try to link here, and we're going to talk about this later, is that what is special about a D10 case. In this case, it happens to be not so special, because what do we know about zinc in terms of color? It's clear, or it's colorless. And the reason it's clear is because all of those d orbitals are completely filled. So that means the electrons can't jump around to that d orbital. It's filled. When we have nickel, where it's a d8, there's an open spot where an electron can move from one d orbital to another d orbital. So it's the relative energies of the d orbitals that just so happen to be in that tiny little sliver of the visible spectrum, and that is going to allow us to start to examine these in terms of color. Okay? Before you leave, this is very important, and some of you have been beating your head against the wall for this. Is it 12 question? Question number 12 on the quiz I'm throwing out. Okay? It kind of got a little more intense than I initially thought. These problems look so innocent on paper, but then you try to go through and you look at them. So you do not need to do number 12. If you want to be bold and adventurous and try number 12, you can do that for extra credit. So I will see everyone in class on Friday. Yeah.